I hope I'm audible.
Yes, sir.
Yes, sir.
Uh, I'm not at my house. I'm in a relative's house because of COVID issue. If there is any problem with the uh, connectivity, internet connectivity, please let me know. Okay.
Okay, sir.
Sir.
I'll share the screen. Just hold on, please. Right. I hope the screen is visible. I'm in slide number 32. Please confirm.
Yes, sir.
Yes, sir.
Okay. So, uh, so what were we discussing in the last class? If someone can summarize what we're discussing. Did we discuss what is a full wave rectifier, center tap full wave rectifier?
Yes, sir.
Did
Yes.
we
Yes,
find
sir.
out its efficiency?
Yes, sir.
Uh, I mean, what is the efficiency of a full wave rectifier? If someone can tell me how much is it?
81.13.
Excellent, 81.3%, right? And that of a half wave rectifier is 40.6, right? And what is the average value of the full wave rectifier output?
2 VM by 5.
Is 2 Vm by pi. Whereas for a half wave rectifier, how much was that?
VM by
Right? And the RMS value for a full wave rectifier is Vm by root 2. And that of a half wave rectifier was Vm by 2, right? And what about the frequency, output frequency? Output frequency of a full wave rectifier is 2 times f, right? If f is the input frequency, then the output frequency of the full wave rectifier is 2 times f. And that of a half wave rectifier is the input frequency and the output frequency are same. Okay. We look at a different rectifier called as a bridge rectifier in today's class. I will just engage your class for 15 to 20 minutes. Okay. The reason being, my in-laws are COVID positive. Okay. I'm there in my in-laws' place and I'm the caretaker for them. Okay. So
Okay, sir.
I need to wind up quickly. Okay. Kindly excuse me for this class. From the
Sorry
next
to disturb.
No problem, sir.
Once again, repeat that frequency, sir.
Yeah, the frequency. See, okay, the frequency of so this is the input which you give for both your rectifiers, right? It's an AC signal, right? Now I'll draw half wave rectifier. Half wave rectifier output would look something like this, right?
Yes.
Right. So if this is how it looks like, how is the output getting repeated? Output is getting repeated at every interval as same as your input waveform, right? Even your input waveform gets repeated the same interval. Whatever green encircle I have done at the waveform, right? Whereas for a full wave rectifier, your output frequency is going to be twice that of input frequency, right? What is this time period? This time period t equals, if this is called as t out, it is equals t in by 2. Am I right? So what would F out be? F out would be 2 times Fn. Am I right?
Yes, sir.
I hope that is understood. Okay. Is that clear? Whoever asked the question?
Yes, sir.
All right. So this is with respect to a half wave and a full wave rectifier. We'll look at a different, a new rectifier today in today's class called as a bridge rectifier. Okay. I'll draw the circuit. I'll tell you the reason why bridge rectifier is used, but I may not be able to completely explain in today's class. Okay, I'll draw the circuit. I hope you're copying down the circuit. Please copy down. Have you copied down? Right. Shall I explain this? I'll probably give you another 30 seconds.
RL or R1, sir.
There is RL, load resistor. Okay.
And it is V0, sir.
Yes, that is V naught. Across the load resistor, you measure the voltage, no? Output voltage. See, either you can do that, or instead of you writing that, you can draw a circuit this way and call this as V naught. Okay. Instead of you drawing this, you can do this also. Doesn't matter. Okay. So what I've done is I've connected this RL there. I hope that is clear. The same way as we did for a full wave center tap rectifier, right? There, I was using a transformer and I tapped at the center. Here, nothing like that is being done. Okay. Let's try to understand the circuit. Then we'll compare all the rectifiers. I'm more comfortable if I draw it in the same figure. Okay. I'll draw it here. RL. This I'm calling it as V0. When you're drawing, please ensure that the diode D1, D2, D3, and D4, the way that you have connected them is perfectly as I have shown here. Okay, if you change the diode direction, obviously circuit itself is wrong. Very important for you to look at the diode anode and cathode values of all the 4 diodes. Okay. All right. Let us analyze the circuit in the positive half cycle. What is going to happen in the positive half cycle? Assume that the diodes are ideal. Okay. Can you tell me which 2 diodes will be on, or will all diodes be on
So
In the
D2 and D4 will be on.
excellent. D2 and D4 diodes will be on in the positive half cycle, right? So that's what I've shown here, plus and minus. So it's in the positive half cycle. In the positive half cycle, the current flow is going to happen in this direction, right? D2 will be on and D4 will be on. Right? If the current flows in this direction, and if the diode is ideal, what would V not be? If diode is
B
ideal,
in, sir.
V in, excellent. If the diode is a silicon diode, what would V on be?
B in minus
V in
1.4.
minus 0.7.
No, it is not 0.7, it is 1.4 as someone else told. Excellent. It is V in minus 1.4. Why is it 1.4? Because the current path is through both the diodes, D2 and D4, right? Right, so
Yes,
V
sir.
naught would be V in minus 1.4 if it is a silicon diode, right? This is what it happens in the positive half cycle. What happens in the negative half cycle? Can someone tell me? See, when D2 and D4 are on, what about D1 and D3? D1 and D3 are off, right? It is very important to tell that also. D1 and D3 are off in positive half cycle, and D2 and D4 are on in positive half cycle. This is for positive half cycle. Can you see me writing? I've written.
So
Is
that
there-
V output is equal to V input is in all cases, sir. Only positive half cycle.
Since we are analyzing only positive half cycle right now, I've told V naught equals V in only in the positive half cycle, right? Since the analysis is only for the positive half cycle, we'll do the analysis in the negative half cycle as well. Let us see. And you know that the current flow is happening from this point to this point, right? If I call this node as A and this node as B, the current flow is happening from A to B in the positive half cycle. Let us see how the current flow in the negative half cycle. I hope the positive half cycle is understood. Is it understood?
Yes, sir.
Yes, sir.
Yes, sir.
So let me show in the negative half cycle what happens. So in the negative half cycle, this is your plus and this is minus. Which two diodes are on in the negative half cycle?
D1 and D3, sir.
D1 and D3 would be on. If D1 and D3 is on, what is the current direction? Current direction would be this. Am I right? Again, I'll
Yes, sir.
show in red color. This is how the current would flow. How is the current flowing? From the same direction as in the positive half cycle. That is from terminal A to terminal B, right? It did not change, right? Both in the positive and the negative half cycle, as happened in the center tapped full wave rectifier. Even in the center tapped full wave rectifier, the current was flowing from A to B. Even here, the current is flowing from A to B, right?
Yes, sir.
Right. So again, what would the output be if it is a what do you call ideal diode? It's an ideal diode. V naught would be equals Vn, and if it's a practical diode, which is if you're using a silicon diode, you end up getting V naught to be equals V in minus 1.4, right?
Yes, sir.
And it is reverse. I mean, D1 and D3 would be on in the negative half cycle, and D2 and D4 would be off. This is for negative half cycle.
So the positive and negative direction will change now, sir, at Vn.
Sorry?
At Vn, the positive and negative has changed now, sir.
Yes, that has changed. That's the reason D3 and D1 are on, no? Because this terminal is positive. If this terminal is positive, D3 is on, right? And if this terminal is negative, then D1 is on, right? So the current flow direction is this. Did you understand?
Yes, sir. Got it.
Sir, V naught for negative half cycle is?
V naught for negative half cycle is same as V in, right? If you're considering it to be an ideal diode, let me draw that, okay? Let me consider as an ideal diode and draw the negative half cycle because some of you are confused. This is open. This is open. And you're giving plus minus V in here, right? If I ask you what is V naught, what would your answer be? I've drawn this, and if I ask you what is V naught, the voltage across the resistor, what would your answer be? V naught is same as V in, right? Because these two are shorted together. I mean, if these two are shorted together, you're giving positive here, which means to say that I can rub this. This is not there. This is also not there. It means this is nothing but, instead of me doing this in a zigzag direction, this is what it means, no? Minus plus V in plus minus V naught. So what is V naught? V naught is same as V in, no?
Yes, sir.
Is that clear?
Yes, sir. Thank you.
If I use
Excuse
a
me.
diode, yes.
Sir, when you share these slides, will you also be sharing the notes along with it?
Notes in the sense, whatever
Yes.
I'm writing here, I'll share that with you. But I really hope that you're copying it down and don't wait for me to share anything.
Yes, sir, we're noting it down, but like since this is a new topic, any additional notes would help.
There will be some slides which I'll share it with you. Okay, since I'm not teaching in the slides, I want to cover the topic fully and then share the slides with you.
Yes, sir. Yes. Okay.
Yeah, but it's very important that you make a notes and don't wait for me to please share the slides. Okay.
Yes.
Don't do that.
Right.
Please.
But,
Yeah. So
sir, we're writing, sir, but sometimes we might miss out on some points. So just in case, we can just make sure when you share the notes.
Right. I will do that. But anyways, since this class is getting recorded as well, I think it shouldn't be a problem, right? Because you can go back and relook at the recording also, right? So this is what happens if the diode is ideal. Okay, so it's the time now. I think I have to leave. Yes, it's 12:05 already. Yeah. So if it is, just hold on a second, okay? Just please hold on. I'll just let them know that I'll come in 2 minutes. Right. So I was just telling, so if you are going to compare this full wave rectifier, center tap full wave rectifier with bridge rectifier, this circuit is called as bridge rectifier. Bridge rectifier. Which one do you think is better from whatever we have discussed now? Here you're getting V naught as V in minus 1.4, but there you're getting V naught as V in minus 0.7, no?
Yes, sir.
Here you're getting 1.4. But why do you think we are discussing this? bridge rectifier when compared to a center tap full wave rectifier? The way of discussion should be whatever is better should be discussed later, right? Here we discussed full wave rectifier, center tap full wave rectifier, and then we are discussing bridge rectifier, right? We'll look at what is the advantage of a bridge rectifier maybe in the next class. Okay. There are some other things before I wind up. Some other things, which is V average. V average of this would be 2 Vm by pi, the same as your full wave rectifier. So if it is a silicon diode, it'll be Vm minus 1.4 divided by pi. Okay. There is a very important terminology called as peak inverse voltage. Okay.
Sir, your screen got stuck.
Okay. Okay. How about now? Just hold on. I am in 36th slide. Can you see?
36 only, sir, but VA is only visible, sir.
For everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, in any case, anyways, I'll wind up now. So since I'm audible, I'll just tell. So there is a very important concept called as peak inverse voltage. Okay. So peak inverse voltage is something which I'll define in the next class and tell why is a bridge rectifier better than a center tap full wave rectifier. Okay. As of now, from whatever you can see, as a layman, from whatever I have explained, it seems that the center tap full wave rectifier is better than bridge rectifier because you are able to design a rectifier only with 2 diodes. Here in a bridge rectifier, you're using 4 diodes. And the output loss, if you look at the bridge rectifier, is much higher than that of a center tap full wave rectifier. But I will prove in the next class that a bridge rectifier is much better than a center tap full wave rectifier. Why is bridge rectifier better than a center tap full wave rectifier? All right.
Sir,
Yes.
sir, also what is the VRMS value of these bridge rectifiers?
Wouldn't that be the same? Because the output is exactly the same, no, as that of a center tap full wave rectifier, right? There is no change.
So VM by root 2 itself must.
Yes, it will be Vm by root 2. Ideally, practically, it will be Vm minus 1.4 by root 2.
Yes.
See, V average and VRMS, wouldn't that be same as the full wave center tap full wave rectifier? Because the waveform exactly is same, right?
Yes, sir.
Instead of minus 0.7, you just have to input 1.4. Am I right?
Yes, sir.
Sorry, I have to stop now. Okay. I'll continue in the next class, which is tomorrow. Tomorrow first hour, right?
Yes, sir.
Okay.
Thank you, sir. No problem.
Thank you, sir.
Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
I
Thank you,
hope
sir.
you feel safe. No issues, right?
No, no, sir. No
Okay.
issues. Thank you, sir. Take care, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Take
Thank
care.
you.